Organic Chemistry, Chem 212, Exam 5 Material, Part 2. Structure Determination using Nuclear Magnetic Resonance Spectroscopy. The use of NMR spectroscopy. It's used to determine relative locations of atoms within a molecule. It maps out the carbon-hydrogen framework of the molecule. It's one of the most helpful spectroscopic techniques used in organic chemistry. It is related to MRI in medicine, also known as magnetic resonance imaging. And NMR depends on a very, very strong magnetic field. For proton NMR or carbon NMR, the nucleus spins and the internal magnetic field aligns parallel to or against an aligned external magnetic field. What we see in this illustration is before the magnetic field is applied, and we can see that the spin is in all different directions. But once the magnetic field is applied, either they're going to go with the magnetic field or against. Parallel orientation is in lower energy, making the spin state more populated. This illustration also shows us that the ones going with a magnetic field, it's showing more of those than in the opposite spin. When we have them parallel to the applied field, it's plus 1/2, that's the lower energy, and when it's opposed to the applied field, negative 1/2. Radio energy of exactly correct frequency or resonance causes nuclei to flip to an anti-parallel state. The energy needed is related to the molecular environment, which is proportional to the field strength B. The stronger the magnetic field applied, the greater the energy difference. NMR detects these small excess nuclei in the lower spin state. It's these energy differences that are measured as the magnetic field is applied. We can see the difference here between those going with the applied field and those against is a little bit smaller than when we have a stronger magnetic field. The nature of NMR absorptions. Electrons in bonds shield nuclei from magnetic field. Different signals appear for nuclei in different environments. In this top spectrum, this is a proton NMR. On the bottom, it's a carbon NMR, and they are showing it of the same compound. One of the ways you can tell that it's a proton NMR is by looking at the parts per million across the bottom. It usually goes up to about 10 or 12. With a carbon NMR, we're going to see the numbering system completely different, and it goes about 200 or maybe a little bit over 200. Another big difference between proton NMR and carbon NMR is carbon NMR has a lot of noise at the baseline. That's what all these little squibbles are down at the bottom here. Each test is run hundreds and thousands of times, and that way we can increase the signal to noise ratio, and we'll talk about that more later. Both proton and carbon NMR use TMS as a starting point, so they'll go ahead and put that compound in there, and that's what we call 0. When we look at proton NMR, we are looking at different hydrogens in different environments. The one they have in green here is attached to a carbon that is right next door to a carbonyl group. The ones they have in pink here, they are in a different environment. The carbon that it is attached to has an oxygen, then the carbonyl group. So we have 3 identical hydrogens they have in green and a different set of 3 identical to each other in pink. So what we're looking at here are 2 different types of hydrogen. That means we would get 2 different signals. And we can see the signal here at 2 represents the hydrogens here in green. And the signal here at about 3.75, that would be the ones here in pink. Looking at the same compound in terms of different types of carbon, we have a carbon on the left-hand side here, which is in a different environment than the carbon in the middle, carbonyl carbon, versus this one. Since we have 3 different types of carbon, we would expect 3 different signals. And that is what this one's showing us. We have the one in blue here, the one in green here, and the one in pink here. The NMR measurement. The sample is dissolved in a solvent that does not have a signal itself and placed in a long, thin tube. The tube is placed within the gap of a magnet and spun. Radio frequency energy is transmitted and absorption is detected. Species that interconvert to give an average signal can be analyzed to find the rate of conversion. Chemical shifts. The position of each peak is called a chemical shift. The left part, and that would be this side over here, is known as downfield. It is of lower field strength for resonance and has little shielding. The right-hand part is called upfield. It is a higher field strength for resonance and has strong shielding. The chart is calibrated with a reference point using TMS, and that's going to set it at 0, so you can see the TMS peak here. The delta scale is an arbitrary scale where 1 delta is equal to 1 ppm of the spectrometer operating frequency. Carbon-13 NMR spectroscopy, signal averaging, and FT-NMR. Carbon-13 is the only carbon isotope with a nuclear spin, and its abundance in nature is just 1.1%. Most samples are measured using FT-NMR. Repeated accumulation of data and averaging signals, incorporated pulse, and the operation of all signals are obtained simultaneously using a broad pulse of energy and resonance recording. Signal averaging. This is the frequent repeated pulses give many sets of data that are averaged to eliminate noise. On the top spectrum here, we have one run, and you can see a lot of noise, and there's a lot of peaks up above the baseline average here where you can't really tell if that's a carbon reading or not. So what happens is if you go ahead and run this frequently, you can go ahead and make the signal to noise ratio much greater. And then you can see the actual peaks that we're looking at for the different carbons. Characteristics of carbon-13 NMR spectroscopy. Carbon-13 spectroscopy identifies and counts the different number of carbon atoms in a molecule. Most carbon-13 resonance are 0 to 220 parts per million downfield from TMS. Chemical shifts are affected by electronegativity of nearby atoms. Oxygen, nitrogen, halogen decrease electron density and shielding, and this moves the signal further downfield. This illustration shows us the characteristic peaks that we would see for methyl, and this is methylene and CH group, carbon with a halogen, carbon single bonded to nitrogen, carbon single bonded to oxygen, and notice as we get more electronegative, we're being pulled further downfield. Here we have carbon triple bonded. We have carbon triple bonded to nitrogen. We have the aromatic region, alkenes, and carbonyl groups. Remember, these aren't going to be exact numbers, they're going to be in a range, because what's going to happen is if they're bonded to something more electronegative, it's going to cause the signal itself to shift. DEPT, carbon-13 NMR spectroscopy. This is distortionless enhancement by polarization transfer. The number of hydrogens attached to each carbon in a molecule can be determined with this test. Normal spectrum will show all your carbons, and then the DEPT 90 gives a signal only if you have a tertiary carbon. DEPT 135 gives you all the signals, plus you can get signals for primary, tertiary, and even signals for secondary carbons. Uses of carbon-13 NMR spectroscopy. The number one reason why we use it, structure determination. We can also find out the number of non-equivalent carbons, the electronic environment the carbon is in and what it's attached to, and using some other tests, we can even figure out how many protons are attached to it. Proton NMR spectroscopy and proton equivalence. Proton NMR is much more sensitive than carbon-13, and the active nucleus of proton is nearly 100% of the natural absorbance. We can see how many different kinds of non-equivalent hydrogens are in a compound, and each non-equivalent hydrogen will give us a separate signal. Each one of these structures have only one non-equivalent hydrogen, so they would each give us one signal. On benzene, you can see each of these hydrogens are identical to each other. They live in the same environment, so only one signal would be given, and it would be in the aromatic region. On methane, each of these 4 hydrogens are equivalent with one reading, and since there's nothing else on there, this reading would be much less than 1 when we're looking at our delta value. Alkene, we have 4 equivalent hydrogens, so we would have one signal, and it would be in the area where the alkenes are. Ethane, even though we have 6 hydrogens, they're all equivalent to each other, that would be one signal, and because there's nothing else in this, it's just a plain old hydrocarbon, its reading would be pretty close to something below 1 delta value, or 1 part per million. Here I'm showing you where we have a group of different molecules that would give us two signals. So let's see if we can find the two different types of hydrogen. On this molecule, I have a chlorine coming off carbon number 2. What's going to happen is the carbon in the middle here has a single hydrogen attached, and that's a completely different environment than all the other hydrogens. So that would be one signal. As we work our way out on this molecule, you can see on the left-hand side I have 3 hydrogens, and on the right-hand side I have 3 more, but they are an identical environment. And that's because we have free rotation around a single bond through here. The carbon-carbon bonds are alkanes, free rotation, so that means all 6 of these hydrogens on the outside would be equivalent to each other, and so that would only be 2 signals for this molecule. Here we have propane. Again, let's look at the center here. These 2 hydrogens I have coming off carbon number 2 are equivalent to each other, so that would be 1 signal. And then on the terminal carbons, those 6 hydrogens are equivalent to each other. That would be its 2nd signal. Here we have chloro on an ethane. These 2 hydrogens right next to the chloro would have a different signal than these 3 hydrogens on the terminal carbon. In fact, we would expect the 2 that are connected to the carbon that also has the Cl on it to be pulled further downfield than these other ones. This molecule only has 2 signals. Here we have cis-2-butene. These 2 hydrogens that are causing the molecule to be cis are equivalent to each other because what we have coming up on the left-hand side and right-hand side of the carbon-carbon double bond, those are also identical to each other. We will only see 2 different signals, one on the hydrogens attached to the vinyl carbons here, and then the CH3s would also give a 2nd signal. Which one do you predict would be pulled further downfield? Well, the answer would be these 2 hydrogens that are involved in the carbon-carbon double bond here, these vinyl hydrogens. They are pulled further downfield. These 2 compounds each give us 3 signals. On this benzene we have a chloro, and we can see that there's a line of symmetry going straight down the middle here. Each of these that are closest to the chloro would have the same signal as each other. These coming down here that I have in blue would have the same signal, and then as each other, and then this one would have its own signal. That would be 3 different signals. On this alkene, notice I have bromo coming off of one end and a CH3 here. This is a trans situation, and the hydrogen I have on the top left here, it lives in a completely different environment. It's attached to the same carbon that has a bromo on it, completely different environment than this one that's trans to it. Additionally, we have this CH3 we don't want to forget about. These H's also have a signal. Chemical shifts in proton NMR. Proton signals range from about 0 to 10. Lower field signals are when hydrogens are attached to sp2 carbons. Higher field strengths are when they're attached to sp3 carbons. Electronegative atoms attached to an adjacent carbon cause downfield shifts. In your textbook, table 13.2 and 13.3 have a complete list. This is just a few examples here. When we have a hydrogen attached to an sp3 carbon, our reading is usually anywhere between 0 and 1.5. This is the allyl position, one carbon next door to the carbon-carbon double bond. Notice that this hydrogen is pulled a little further downfield. Its reading is somewhere between 1.5 and 2.5. The vinyl hydrogen is even closer to this carbon-carbon double bond, and so we'll have a reading somewhere between about 4.5 to 6.5. Hydrogen on an aromatic, somewhere between 6.5 and 8. And hydrogen on this alpha position next to this carbonyl group, it's still pulled a little further downfield, about 2.2. Now remember, these numbers aren't exact. It's always going to be ranges because other things could be on the molecule that even pull it further downfield. Integration of proton NMR absorptions and proton counting. The relative intensity of a signal, the integrated area, is proportional to the number of protons causing the signal. On the spectrum down here, the integration line is this black line that's coming across, and when it hits a signal, it goes straight up, and then when it gets to the next signal, it goes straight up again. It's the straight up portion that we're going to be looking at relative to each other. This information is used to deduce the structure. So for example, when you have ethanol, the signals are integrated 3 to 2 to 1. Take a look at our structure. We have 3 hydrogens, 2 hydrogens, and 1. Now, this isn't the spectra for ethanol down here. This is just showing you an example ratio. For narrow peaks, the heights are the same as the areas and can be measured with a ruler. Some instruments calculate the number of hydrogens and print it above the peak on the spectra, so you won't get this integration at all. Let's take a look at the integration and how it relates to the structure that it has. All right, if we take a look at this integration line here to here versus the integration line from here to here, if we had a ruler we could be more exact, but I want you to notice that this is about 1/3 of the height of this one. So this reading we have here at about 1.2, this is kind of this green color, it should have 3 more hydrogens than the one here. Well, let's take a look. On this side here we have 3, 6, 9 hydrogens that are equivalent to each other, that are causing the chemical shift or the peak right here at 1.1, 1.2. And then we only have 3 hydrogens that are equivalent to each other, causing this one. Spin-spin splitting in proton NMR spectra. Spin-spin splitting, this is when the peaks are often split into multiple peaks due to the interactions between non-equivalent protons on adjacent carbons. Now, I want you to note that spin-spin splitting happens with proton NMR. It does not happen with carbon NMR. The splitting is into one more peak than the number of hydrogens on the adjacent carbon. This is the n+1 rule. Relative intensities are in proportional of a binomial distribution and are due to interactions between nuclear spins that can have 2 possible alignments with respect to the magnetic field. The set of peaks is called a multiplet. So if you have 2 peaks, we call it a doublet. If there's 3 peaks, we call it a triplet. 4 is a quartet, and so on. Common spin multiplicities. The signal intensity of peak is approximately that of Pascal's triangle. These relative intensities here, if you have a singlet, you'd have 1 peak, a doublet 2, and so those 2 peaks would be the same height as each other. A triplet would have a higher one in the middle, but the 2 on the right-hand side and left-hand side would be about equal height. A quartet, you would have 2 of them the same height as each other, but they're going to be about 3 times higher than the ones on the end, and so on. This is really helpful to keep in mind, this ratio of intensities, when you want to know what peaks belong to what signal and which hydrogens you're looking at. Coupling constant J. The difference in hertz between the centers of peaks in a multiplet, that's what a J value is. A pair or coupled nuclei will have exactly the same J value. This is useful in establishing nearest neighbors in structures. We have one signal here that's been split into a quartet. Notice here we have Pascal's triangle, where these guys are about 3 times taller than the ones on the end. Now, what happens is the distance between each of these split values, that's called the J value. So within one signal, you will have the same J value between all of these different peaks. And that's one way we could tell that these peaks belong together. But here's something that's interesting. If the signal on this one here, that's the CH3, if this signal here has the exact same J value as this one over here, then that tells me they're coupled together. That means they're next door to each other on the molecule. More complex spin-spin splitting patterns. Spectra can be more complex due to the overlapping of signals and multiple non-equivalents. So this spectrum shows us how it can be complex, and what they might do sometimes is they'll go ahead and take some of these signals that are very complex and then bring them out above it so you can see them in more detail. And that's what they did to this section through here, and that's also what they did with this pink one here. The riffing effect, peaks may lean towards each other, and this will tell us that they're coupled with each other, that they're next door to each other. The peaks can lean towards the direction of the larger peak to find a coupled partner. They don't have to be next to each other on the spectrum. The riffing effect is very useful to tell us what protons are next to other protons. So what we have here are 2 examples of riffing effects. Here we have 1, 2, 3 signals here and 2 signals here. This one here that has 3 signals is coupled with this one. How do I know? Take a look at this. We've got what's called the riffing effect. Do you see how instead of having our Pascal's shape happening, we have it kind of tilted as a riff towards each other? So we still have 2 signals here, but it's pointing to this guy, and the riffing effect is pointing to this one here. So that's how I know they're coupled with each other. Here's an example of a 4-3 situation. This one is coupled. Let's bring that line here. And this one is coupled. This is the riffing effect. Again, a nice way for us to help put together our structure. Uses of Proton NMR spectroscopy. The technique is used to identify likely products in the laboratory very quickly and easily. For example, we can also look at the regiochemistry of hydroboration and the oxidation of methylene cyclohexane. So what we're looking at here is during this reaction here, are we going to get this product or this product out of it? Well, we've got addition across the double bond. That's what's going to happen. We have H and OH adding across the double bond. And when we take a look, if we want to know which one we have, when we have the methyl group on the end here with the OH, what happens is we get a really nice signal here at about 3.5 that is from the two hydrogens connected next to the alcohol group. Whereas when we have this one, our reading is just a CH3 group. It's not attached to a carbon that also has an oxygen. It's not pulled further downfield. It's this hydrogen here that's on the same carbon as an OH that pulls it further downfield. And then we can tell which compound we have. Conjugated dienes and UV spectroscopy. Conjugated and non-conjugated dienes. Compounds can have more than one double or triple bond. If they are separated by only one single bond, they are conjugated and their orbitals interact. The conjugated diene 1,3-butadiene, shown here, has properties that are very different from those of the non-conjugated 1,4-pentadiene. Conjugated dienes are more stable than non-conjugated based on heats of hydration. Polyenes. Compounds with many alternating single and double bonds are known as polyenes. The extended conjugation leads to the absorption of visible light, producing color. Conjugated hydrocarbons with many double bonds are polyenes. Here we have an example of lycopene, which is responsible for the red color in tomatoes. Extended conjugation in ketones, or enones, are found in hormones such as progesterone. Preparation and stability of conjugated dienes. Base-induced elimination of HX in an allylic halide will produce, in this case, a 1,3-cyclohexadiene. We have our carbon-carbon double bond here. NBS is very selective. If you remember, that actually puts the bromo on the allyl position. This set of reagents will cause an elimination reaction to happen, and now we have a conjugated system here. Another way to prepare a conjugated diene, this is the industry synthesis by cracking, and the product is used to make polymers. Go ahead and make sure that you have a degrees C sign here. Remember, for some reason when I have it on my Mac, I get an infinity sign, so this is 600 degrees C in a catalyst, and this cracking method produces a conjugated diene. Looking at the molecular orbital description of a 1,3-butadiene. The single bond between the conjugated double bond is shorter and stronger than an sp3 bond. The bonding pi orbitals are made from 4 p orbitals that provide greater delocalization and lower energy than an isolated carbon-carbon double bond. The 4 molecular orbitals include fewer total nodes than in the isolated case. In addition, the single bond between the two double bonds is strengthened by the overlap of the p orbitals. In summary, we say electrons in 1,3-butadiene are delocalized over the entire pi bond system, and delocalization leads to stabilization. This illustration is showing us the delocalization of the 1,3-butadiene, the conjugated system. You can see that this piece right in here where the double bond isn't is actually also participating in the overall pi system. Electrophilic additions to conjugated dienes. Allylic carbocations. Allylic carbocations are more stable than tertiary carbocations. Here's a structure of an allylic carbocation, and this is what a tertiary carbocation looks like. Electrophilic addition reaction with conjugated dienes yields a mixture of products. In this reaction here, we see we have a primary carbocation, and what's going to happen through resonance is our carbon-carbon double bond is going to shift to form a secondary carbocation. Now, the secondary carbocation is going to be more stable, so it'll be in greater abundance. Let's take a look at what products can form when we bring bromine in. When bromine comes in, and we have a primary carbocation, did you notice that we get about 29% in the 1,4 addition versus when we have the secondary carbocation, we get a 71% yield. Kinetic versus thermodynamic control of reactions. Thermodynamic control, an equilibrium reaction that yields the lowest energy, most stable product. This is done at higher temperatures, under more rigorous conditions, and is a reversible reaction. Kinetic control, a reaction that follows the lowest activation energy pathway. The product is the most rapidly formed, but not necessarily the most stable. This is done at lower temperatures, milder conditions, and irreversible. Equilibrium is not reached. Kinetic and thermodynamic control example. Addition to a conjugated diene at or below room temperature normally leads to a mixture of products in which the 1,2 adduct predominates over the 1,4 adduct. Let me go ahead and just interject here. The word adduct is from a combination of the word addition and product. Adduct is the product you get from an addition reaction, so they call it adduct, addition product. They just took the two words and smushed them together. That's what an adduct is. At higher temperature, the product ratio changes and 1,4 adduct predominates. So let's take a look at this illustration here. They're showing us we have a conjugated system here, and if we do this reaction at 0 degrees, we get 71% of the 1,2 and only 29% of the 1,4 product. But if we go ahead and heat this thing up, we can change which one we get predominantly. In fact, if we do this at 40 degrees, we only get about 15% of the 1,2 adduct and about 85% of the 1,4. Diene polymers, natural and synthetic rubber. Conjugated dienes can be polymerized. Diene polymers are structurally more complex than simple alkene polymers because the double bonds remain at every 4 carbon atom along the chain. There's also the possibility of cis and trans isomers. Here we have the structure of a cis polybutadiene and trans polybutadiene. Natural rubber. It's a material from latex and it's found in plant sap. In natural rubber, we have repeating units of 5 carbons, and it has Z stereochemistry at all the carbon-carbon double bonds. So here we have a picture here of 2 monomers making up our polymer. Natural and synthetic rubbers are too soft to be used in products unless they're hardened by the process called vulcanization, a technique used to cross-link the chains. Charles Goodyear, yes, of Goodyear Tire Company, discovered heating with small amounts of sulfur produces a strong material. These sulfurs form bridges between the hydrocarbon chains and cause cross-links. So we can see the natural rubber polymer here, and these are the disulfide bonds that help bring them together. And this makes a much stronger material. Synthetic rubber. Well, here's an example of neoprene. We've seen neoprene around a lot now. The chemical polymerization of isoprene does not produce rubber. Stereochemistry is not controlled. Synthetic alternatives include neoprene, a polymer of 3-chloro-1,3-butadiene. Neoprene, it resists weather and is much better than rubber. Here we have 2 different molecules here coming together. They're showing us where the electrons are going. We have an initiator here starting this. And so here's a picture of part of our polymer here. It also is in the Z stereochemistry. The Diels-Alder Cycloaddition reaction. Conjugated dienes can combine with alkenes to form a 6-membered cyclic compound. The formation of the rings involves no intermediate. It's concerted. The formation of the 2 bonds happen all at the same time. This was discovered by Otto Paul Hermann Diels and Kurt Alder in Germany in the 1930s. So let's take a closer look at what's happening. We have our conjugated diene and we also have our alkene. When the alkene comes closer, they start electronically being attracted to each other, and all this is going to happen at one time. That's what the concerted is. So we have a carbon here and a carbon here. Well, if this pair of electrons comes down here to form a single bond between this carbon and this pair of electrons does not want to stay there. because that's too many electrons next to that carbon, too many bonds, so it's going to form its bond here. The double bond that was here is going to now form the actual bond between this carbon, and the only double bond that remains is this guy right here. These two bonds here I have in this light green color came from the electrons from the carbon-carbon double bond from the alkene that came in. Now, we're going to be seeing this reaction where it's not just a plain old alkene. Sometimes there's going to be other things attached to it. So let's look at an example here. Here we have our 1,3-butadiene, and then here's our carbon-carbon double bond coming in. So what's going to happen is this carbon is going to now be bonded here. The double bond's going to go here, and this is going to form the bond between this carbon and this carbon. But this little piece here, it remains. It doesn't change. It's still bonded to the same carbon. Why don't I go ahead and number these carbons? Now, this numbering system has nothing to do with naming. Let me number these carbons, and maybe we can follow these a little easier. So what I did is I went ahead and numbered this carbon 1, 2, 3, 4, 5, and 6. So what we have here, this would be carbon 1, 2, 3, 4. There's carbon 5, and there's carbon 6. Notice this carbonyl group here is attached to carbon 5, and it's still attached to carbon 5. There's no change here. Characteristics of the Diels-Alder reaction. The alkene component is called the dienophile, a diene lover. The reaction proceeds rapidly and is in high yield if the alkene is conjugated to an electron withdrawing group, such as a carbonyl group or a nitrile. Alkynes, triple bonds, can also be dienophiles. Here we have our ethylene, which is basically not very reactive. They're even calling it unreactive in the Diels-Alder. This would be examples of our alkene. The alkene example we showed on the previous slide had this carbonyl group, and we can see that it helps the electronic structure of this with this oxygen here pulling some of the electron cloud towards it. We see the dipole moment moving in this way. This one happens to be a cyclic alkene. Even though it's got all this other stuff going on, this is where the attachment would be on what we had labeled as carbon 5 and 6. And also here, this is also going to be acting like an alkene, where the carbon-carbon double bond here is going to be carbon 5 and 6 as we had earlier, and the rest of this will just follow. Stereospecificity of the Diels-Alder reaction. The reaction is stereospecific, maintaining relative relationship from reactant to product. When you start off with a cis-alkene, you get a cis product. Transalkene gives you a trans product. Here's a couple of examples of that. Remember, here's our diene, and this is our alkene. When the alkene is cis, you get a cis product. When the alkene is trans, you get a trans product. In order for the diene to work in a Diels-Alder, it must adopt an S-cis configuration, or an cis-like, around the carbon 2 and carbon 3 single bond. We have free rotation around the carbon number 2 and 3 here, because we have a carbon-carbon single bond. So what happens is it must be in this orientation here, where we have this bond angle happening, in order for the reaction to happen. If it were in this conformation, for example, the reaction wouldn't happen. This is what's meant by cis-like. It's not technically cis, because there's not a carbon-carbon double bond here, but you can see where they're coming at in that term, that this part is cis relative to each other. Structural determination in conjugated systems, UV spectroscopy. UV is applicable only in conjugated systems. That's why we've been talking about them earlier. The UV region of greatest interest to organic chemists is the 2 × 10⁻⁷ meter to 4 × 10⁷ meter, or 200 to 400 nanometer range. What gives us the signal in UV spectroscopy? Well, this is when the electrons in the highest molecular orbital, HOMO, undergo a transition to the lowest unoccupied molecular orbital, LUMO, and that is what's being detected. UV spectroscopy is a plot of the absorbance, log of the ratio of the intensity of light in over light transmitted against wavelength in this region is known as the ultraviolet spectrum. In this example, we can see we have just one peak, and the peak right here is at 217. The ultraviolet spectrum of 1,3-butadiene, it is a conjugated system, the same one we've been talking about. So this example, we have 4 pi molecular orbitals with the lowest 2 occupied. The electronic transition is from HOMO to LUMO at 217 nanometers, and the peak is broad because of a combination of bending and stretching. Here we have our 4p atomic orbitals, and what's going to happen is we have the bottom filled with 1 and 2, remember opposite spin. We only have 4 total, so we have these 2 also in here. When we apply UV radiation, it's going to cause one of these to jump. This is in its highest molecular orbital to the lowest unoccupied molecular orbital. That's this one here. It's this energy difference here that we're able to see in our spectra. Quantitative use of UV spectra. Molar absorptivity, the exact amount of UV light absorbed in a sample. This is a physical constant, similar to density or melting points, and it's characteristic of a particular sample. You can follow changes in concentration with time by recording absorbance at the wavelength. Using Beer's law, where absorbance is equal to the molar absorptivity times its concentration times the path length. You most likely did these style of calculations back in general chemistry during some of your lab experiments. Interpreting UV spectra, the effect of conjugation. Lambda max is the wavelength where UV absorbance for a compound is the greatest. The energy difference between HOMO and LUMO decreases as the extent of conjugation increases. Lambda max increases as conjugation increases. 1,3-butadiene has a reading at 217 nanometers, whereas 1,3,5-hexatriene, another conjugated system, is at 258 nanometers. Substituents on the pi system can also increase lambda max. Conjugation, color, and the chemistry of vision. Most organic compounds are colorless, but a few are colored, and the visible region is 400 to 800 nanometers. Extended systems of conjugation absorb in the visible region. Beta-carotene has 11 double bonds in conjugation, and its lambda max is 455 nanometers.